Today we're going to talk about properties of solutions and then also properties of other mixtures like colloids and suspensions and how those can change properties of our solution. So let's talk now about what colloids and suspensions are. So if you remember, a solution is a mixture where the particles are actually the size of ions or molecules. They break apart completely and are surrounded by solvent molecules. In a colloid, the solute particles are much larger. And it's still a homogeneous mixture, but the particles are much bigger than just a single molecule or ion. So some examples of colloids are fog, mayonnaise is a common example. Some kinds of cheese are colloids. Jello is a colloid. Whipped cream is an example. So there's lots of different examples that you come into contact with in everyday life that are colloids. Suspensions are heterogeneous mixtures. That means they're non-uniform, and they have very, very large particles, even larger than in colloids. And as a result, they settle out of solution settle out of the mixture when you let them sit. So some examples of this might be muddy water or sandy water. Mustard is one example of this. Some salad dressings, like an oil and vinegar salad dressing, would be a suspension. Some medicines that we get are suspensions, so you can mix them up and they become kind of uniform, but then you let them sit and they settle out. So let's summarize these properties in a little table here. So in a solution, the particles are very small. They're either atoms, ions, or small molecules. Okay. In a solution, the particles do not settle, and they cannot be separated out by either filters or a semi-permeable membrane. And I'll talk a little bit about what that means on the next slide. So colloids, as I said, are larger. The particles are larger than they are in solutions. And they're usually groups of molecules or ions that are sort of stuck together. And these do not settle either. So if you let the mayonnaise sit in your fridge for weeks, it's still a uniform solution when you pull it out, right? And then these particles are big enough that they can be separated by a semi-permeable membrane, but not by filters. So a filter would filter out bigger particles. All right, and then a suspension is the largest of the particles, so much so that they are visible to the naked eye. The particles settle fairly rapidly, and then these particles can be separated out by filters. So let's take a look at this in terms of a diagram for what this means. So in terms of settling, we're representing our suspension here with squares. So it settles out of solution, settles out of the mixture, whereas colloid, which is the triangles, and solutions, which are circles, are still floating in the mixture up above here. They don't settle. Okay, so if we use a filter, if we pour our solution, colloid, and suspension in the filter, you'll find that the filter keeps the suspension, all the squares stay up here, and the other bits are small enough that they go through the filter. So this would make sense if you were to filter muddy water, for example. The particles of dirt are going to be big enough that they're going to be stopped by something like filter paper. All right, and then the last thing would be a semi-permeable membrane. So with a semi-permeable membrane, there's not a lot of space. They're very small pores. And so the only thing that's going to escape through the semi-permeable membrane will be the particles in the solution, which are the atoms or molecules. All right. So now if we make these mixtures, we can change the properties of our solvent. So for example, if we were to dissolve something in water, that is going to change some of its properties when we do that. So that's what a colligative property is. A colligative property is a physical property that will change depending on the number of solute particles in your solution. So the more solute particles you have, the larger the change in that particular property. So freezing point and boiling point are the two we're going to talk about in terms of colligative properties. Those are the two that we're going to discuss that change when you add a solute. And so if we add a strong electrolyte, if you remember, a strong electrolyte divides up completely into its ions. So a strong electrolyte is going to have the largest effect on these colligative properties. So it will change the freezing point the most, okay? So that would be the answer to this question, which is going to change the freezing point the most. It would be the strong electrolyte. The non-electrolyte doesn't break apart at all. So each one you put in only becomes one. Whereas the strong electrolyte, if it was sodium chloride, for example, every sodium chloride you put in, you're going to get sodium and a chloride ion, so that's going to give you two. A weak electrolyte dissociates to some extent, but not completely, and so that will be intermediate between the non-electrolyte and the strong electrolyte in terms of its effect. Okay, so why does dissolving particles in water cause the freezing point to go down? So I mentioned that the freezing point changes when we dissolve something in water, but why is that? And it actually goes down, so the direction is important as well. And the reason is, so if we think about putting additional particles into our water, this would be what ice looks like when the water particles or water molecules are all aligned in a solid form. But if we stick something else in there, like an ion, for example, in this case, it's going to disrupt that structure. So it's going to be even harder for it to make that organized array that it needs to make to become a solid. And so we're going to need to make it even colder in order to get that order to happen. So that's why if we dissolve particles in there, then we have to make it even colder to make it a solid, so the freezing point is going to go down. And we're going to do a lab with that in class this week that you'll see that effect. Okay, the other colligative property that we're talking about in this chapter is the boiling point. So dissolving particles in water actually causes the boiling point to go up. Okay, so if this is our liquid water here on the particle level, all of these molecules are interacting via hydrogen bonds, right? If we dissolve something in that water, now the water molecules are interacting with each other to some extent, but they're also interacting with, in this case, this positive ion that we've dissolved. And so what happens is that there's an attraction there that's even stronger than the attraction between the water molecules themselves. And so the result is, in order for, say, this molecule here to break off, we have to hit it or heat it even hotter and give it more kinetic energy to overcome that attraction that it has to that ion. So when we dissolve additional particles, we create additional attractions, and so we need to overcome those using more heat. So we need to heat it up more in order to get to the boiling point. All right, so that sums up, or that wraps up our discussion of the properties of solutions. And we're going to do some labs with these in the rest of the week and a little more practice in mastering chemistry.